Hello, and welcome to the ENSC 1004 Corrosion Lab. In this lab, we will focus on the corrosion of mild steel in a number of corrosive environments. Specifically, in Experiment 1, we will visually inspect steel coupons that have been in an aerated acidic solution for 7 days, clean the coupons, and then weigh them to determine the mass loss over that period of time. In a second experiment, we will make a galvanic corrosion cell using a solution of 0.1 molar aqueous potassium iodide as the electrolyte with mild steel and zinc as the galvanic couple. This is the corrosion studies kit. Some of the corrosion cells are aerated. The sound you can hear is the air pump. The electrolyte solutions in the corrosion cells are, from left to right, deionized water, 0.1 molar potassium iodide solution, which is used as a stand-in for tap water, deoxygenated sodium chloride solution at 35 grams per liter, which is similar to seawater, an aerated sodium chloride solution of the same concentration, a buffer solution of pH 4, which is representative of a dilute acidic environment, and lastly, a galvanic cell with 0.1 molar potassium iodide solution and galvanic couples formed from mild steel and copper. On top, the cells have had the positions of the steel coupons labeled. The pH 4 buffer solution started clear and became progressively darker during the experiment. With the aid of this backlight, you can see that the solution is not cloudy, as would be the case if they were suspended solids, but the solution itself has simply become a dark reddish color. This is a photo of the pH 4 buffer cell alongside a close-up of a coupon in the pH 4 cell. These photos were taken 5 days into the experiment when the solution was a little lighter in color and it was still possible to see into the cell. The analysis of coupons in the pH 4 buffer corrosion cell begins with the removal of a single coupon from the cell. The coupon is photographed on both sides. Next, the coupon must be cleaned of corrosion products. The cleaning supplies include ethanol, a couple of beakers, deionized water in a squirt bottle, a drying rack for use after the sample is clean, a deep tray to keep things tidy, and a brass wire brush. The corrosion products will be removed from the coupon with the brass wire brush. Brass is softer than steel, so there is no chance of scraping away any of the metal from the coupon. The corrosion products are loosely attached to the mild steel, and the brush should be able to scrape them away. The water will help to wash away the corrosion products from the coupon after the brush has loosened them. Finally, the ethanol will speed up drying of the coupons. Cleaning the coupons takes some time, and it's important to be careful so as not to scratch off the black plastic coating on the coupons. Parts of the video have been sped up so as not to be tedious. Once a coupon is clean, it can be moved to the drying rack. After a few minutes in the drying rack, the coupon is given a final thorough drying with a hairdryer set to medium heat. Finally, the coupon is weighed. This series of steps, photographing, cleaning, drying, and weighing, must now be repeated twice more for the 2 other coupons. The mass of all 3 coupons has been recorded and provided to you in an Excel spreadsheet on LMS, along with the initial masses. In the second experiment of this lab, we must make up a 500 milliliter solution of 0.1 molar potassium iodide. To do that, the analytical balance is used to weigh out 8.35 grams of dry potassium iodide. Any excess must be discarded and should never go back into the original reagent container to maintain its purity. Next, the potassium iodide must be transferred into a 500 milliliter volumetric flask. The weighing paper can be used as a funnel to ensure no potassium iodide is spilled. Deionized water is added to the flask until it is about half full. The solution in the flask is swirled until the potassium iodide is completely dissolved. Then, more water is added until the water level reaches the neck of the flask. To bring the water level up to precisely 500 milliliters, more water is added slowly by pipette until the bottom of the meniscus reaches the fill line. The corrosion cell we are making consists of steel-zinc galvanic couples. First, the mild steel coupons are inserted into the lid of the cell in the marked positions. Then, the zinc coupons are inserted in between the steel coupons. Finally, the lid is placed on the beaker, immersing the coupons in the potassium iodide solution. The current voltage of each galvanic couple can be read using a multimeter. Part of the circuit in a galvanic cell carries charge via the migration of ions in solution. It takes about 5 to 10 minutes for the diffusion of ions in the electrolyte solution to reach a steady rate, and during this time current and voltage will continue to change. Stable values for the current and voltage for 3 steel-zinc galvanic pairs have been provided to you in an Excel spreadsheet on LMS. Values for 3 steel-copper galvanic pairs have also been provided in the same spreadsheet on LMS. When the multimeter is connected to a pair of mild steel coupons, the voltage and current are seen to be very low. Similarly, when the multimeter is connected to a pair of zinc coupons, the current and voltage are both very low. Thank you for watching, and good luck with the lab write-up.